Hello, I apologize for not being able to make it to class. As I said in my email, I've been looking to try to find a babysitter, childcare for Wednesday night, and it's just hard whenever the schedule changes like that. My wife works Wednesday nights, and I'm sure some of you might have had some difficulty trying to rearrange your schedule too. So hopefully, after this week, we'll have smooth sailing to the end of the semester, because I know we were disrupted, two weeks ago as well. So, anyways, we're going to pick up with geologic dating. Now, in lecture, we were uh, finishing up talking about relative dating, and we moved on to radioactive dating. And just to kind of review a little bit, radioactive dating is a technique to absolute date rocks. Is we igneous rocks, that is we use the uh, the fact that radioactive atoms or radioactive materials are found in trace amounts in pretty much all Earth materials, and that these radioactive or unstable atoms, they decay away or break down at a predictable rate, and we quantify that rate with what's called the half-life, and the half-life is the amount of time required for half of a given amount of a radioactive substance to decay away. And so we call the radioactive atom the parent, so the unstable parent, and whenever it breaks down or decays, it forms stable atoms known as the stable daughters. And so initially, if you look at this chart right here, initially at time t equals 0, we have 100% radioactive parent atoms, and we have 0 stable daughters. Now, on the x-axis here are the number of elapsed half-lives. And so we start off with at 0 half-lives, 0 daughter, and 100% parent. After 1 half-life, half of the original 100% of the unstable parent decays away, so we have 50% remaining. And at 50% that decayed away, they became stable daughters. So we have 50-50 parent and daughter atoms. Then after another half-life, half of that 50 remaining radioactive atoms decays away, so we have 25. And that 25, the difference between 50 and 25, those 25 radioactive parent atoms, they decayed into stable daughters. So now we have 50 plus 25 more daughters, totaling 75. So now the ratio of parent to daughter atoms is 25 to 75, the ratio of daughter to parent is 75 to 25, which is 3 to 1. After another half-life, if we half of 25 is 12 and a half, but you can have a half an atom, so 13 atoms here. All right, and then those atoms that decayed away here, they form stable daughters. Now we have 87 stable daughters and 13 unstable parents after 3 half-lives. So here the ratio is 87 to 13, or basically 7 to 1. And so whenever geologists, they want to date how old a rock is, they'll go out and they'll take several mineral crystals from a unit of bedrock. Say from a piece of granite, they'll take a feldspar, quartz, and hornblende crystals from various parts of the outcrop. Then they use an instrument called a mass spectrometer that allows them to measure the relative amounts of different elements and even the different isotopes of those elements. And that's how they measure how much daughter and parent atoms are present, and they get this daughter to parent ratio. Once they know this, how many daughters and parents are present, that allows them to determine the number of elapsed half-lives. And once they have the number of elapsed half-lives, all they need to do then is then multiply the number of elapsed half-lives by the length of the half-life of that parent-daughter pair. So for example, a very common parent-daughter pair is uranium-235. It decays into the stable daughter lead-207. And the half-life of that parent-daughter pair is 704 million years. So let's say if we had a granite and we analyzed it, and the daughter-to-parent ratio came out to be 3 to 1. That means there was 75 daughters and 25 parents. That would tell us that 2 half-lives have elapsed, and they would multiply that number by the length of one half-life, 704 million years, and so that would give us 1,408 million years, or 1.4 billion years. So this is how geologists determine the absolute age of the rock. Now, igneous rock is the only type of rock which we can perform this technique on. If we would perform on a sedimentary rock, if we took several mineral crystals from a sedimentary rock, we could find the absolute ages of when those mineral crystals solidified from melt. But the problem is that they came from those sediment weathered out of bedrock from all over, and so we get ages all over the place, and we wouldn't find the actual age in which the sedimentary rock itself formed. We would find the ages at which the mineral crystals themselves form. And same thing with metamorphic rocks. We can't use radiometric dating to determine the absolute age of metamorphic rocks. However, if we know the age of the event that caused the metamorphism, say we know the age of an igneous rock, or the igneous intrusion that formed the igneous rock, it thermally metamorphosed the nearby host rock, well then we know the age of the igneous rock, so therefore we know the age of the metamorphic rock around it. So here's an example of how we can use absolute dating in tandem with relative dating to get some idea of the absolute age of sedimentary rocks. In this geologic cross-section lower left, we have a batholith down at the bottom. Let me get the pen up here. This batholith down at the bottom is 180 million years old. We have beds of sedimentary rock above it, and then we have a dike cutting through them. Now the dike and the batholith being igneous rocks, we can find their absolute age. As I said, the batholith is 180 million years old. The dike is 150 million years old. Now relative dating, the principle of superposition tells us that these sedimentary rocks being laid over top of this batholith must be younger than that batholith. So these sedimentary rocks must be younger than 180 million years old. And the principle of cross-cutting relationships tells us that this dike, since it cuts across these sedimentary rocks, the dike must be younger than the sedimentary rock. So therefore, the sedimentary rock must be older than 150 million years. So this gives us this bracket in absolute time within which these sedimentary rocks had to form, 150 to 180 million years ago. And in this cross-section on the right, we have these sedimentary rocks that were regionally metamorphosed during a continental-continental collision that occurred at a known date, 750 million years ago, so we can ascribe that absolute age to these metamorphic rocks. So we know the age of these metamorphic rocks. However, these sedimentary rocks above it are of unknown age, but here's an ash fall. That's igneous material, so it can be absolute dated. We find that it is 675 million years old. Above it, more sedimentary rocks, and on the very top we have a lava flow. Igneous is dated to 600 million years old. So these sedimentary rocks here must be younger than the metamorphic rock below it, but older than the ash fall above it. So that puts them between 675 and 750 million years old. And these sedimentary rocks must be older than the 675 million year old ash fall below them. Must be younger, than the 675 million year old ash fall below them, but older than the 600 million year old lava flow on top of them, giving them an absolute age range of 600 to 675 million years old. What happens if there is no igneous rock or metamorphic rock of known age near the sedimentary rock in which you can use the principles of relative dating to determine its age? Well then, if we have sedimentary rock of one location, say location A, which we know the absolute ages of this, then if we could draw time equivalencies between the rocks at location B and C, which is, say, no reference in time, there's no igneous rock at B and C, if we can somehow draw time equivalencies between the rocks at A and those at B and those at C, then we can map the absolute ages of the sedimentary rock at A to those at B and C. And so this drawing or determining that two units of sedimentary rock in two different locations were formed at the same time, that's called correlating rock units. And one way in which we correlate rock units is using the fossils found in those sedimentary rocks. So, so majority of the species that have lived on the planet are extinct. Over 99% of all species that have lived on Earth are now extinct. So extinction is the status quo. So there's many species in the fossil record that, well, all species in the fossil record pretty much have gone extinct except for a few, but they all come into existence through evolution, and then they go out of existence through extinction. And so they're only around for some finite period of time in the geologic past. And so the fossils that are present in a sedimentary rock reflect or give some information as to when that rock formed. That rock had to have formed at some time in Earth's past, during which all of the species that are fossilized in that rock were simultaneously present. And so let's say these rocks at location A, they're of known age. So we've somehow been able to determine the absolute age of these rocks. Well, these lower rocks on rock A, down here, they have these fossils found in them, a crinoid, sort of oyster, and a trilobite. Those same fossils are found in these rocks at location B. Well, because these same fossils are found in these rocks at location B, chances are they formed at the same time as these rocks over here at A did. So we can map this age of these rocks at A over to these rocks at B, and for the same reason over to these rocks at C, which contain the same fossils. Okay, but these rocks down here at location C, they have fossils not found in A. So we know that these rocks at C must be older than these rocks over here at A. And then these sedimentary rocks, these upper ones at location A, they have these fossils present in them, as do these rocks at location B, so we can map this absolute age from A to B and also to C. But you can see that these rocks up here in B, these uppermost rocks, they have fossils in them that are not found in A, so we know that the age of this rock in B must be younger than these rocks A and have not formed at the same time, containing different fossils. Excuse me. So what if we can't even correlate rock units? Maybe we have no references, we're not even nearby sedimentary rock of known age. How do we determine the absolute age of sedimentary rock? Well, we can use this idea of fossil succession. Like I said earlier, species come into existence in Earth's history through evolution and they go extinct. And so the species that are fossilized in a sedimentary rock kind of act as a unique identifier in time. So we reference the paleontological record, which there's a little simplistic example of it over here on the right, which indicates what range in time different species existed on the planet based on the paleontological record. And so we look at a rock unit, say like rock unit A, has these these fossils found in it. Sorry. And we look at the paleontological record and say, well, what period in time did all of these species simultaneously exist on the planet? And so you see this sliver in time highlighted by the pink line. It has all of these all of these fossils present during this time. And so this is the only time which this rock could have formed, because this time span is the only time in geologic past in which all of these species were simultaneously present on the planet. And here we have the same thing applied to rock unit B, where it's this time swath. Sorry, let's update. It's this time swath in which all these fossils are simultaneously present. Okay, so we can use this idea of fossil succession to come to some conclusion of the absolute age of sedimentary rock if we have no known reference in absolute time. So we have no nearby igneous rock or metamorphic rock of known age, and we cannot correlate this sedimentary rock with any other sedimentary rock of known age around in the area. So we can use fossil succession to come to some conclusion about the absolute age of sedimentary rock in that case. So another useful tool in determining the age of rock is using what's called key beds or marker beds. A key bed or a marker bed is a bed of rock that is of known age. Um, so often it's a datable layer, like igneous layer, that's present over a large geographic area. And so an example of a key bed or marker bed would be a large volcanic eruption, which produces a large ash fall that covers a large geographic area with a layer of ash. Now that layer of ash, um, once in the geologic strata, anytime that layer of ash is found, that provides a reference in absolute time in the geologic strata, or the layers of rock. And so that's why it acts as a key bed. So you can go to different parts of, say, North America and look at exposed sedimentary rock, and you see these different ash falls from Yellowstone, and you know exactly when in the geologic past you're looking at. You find those beds. A very famous one is the KT boundary. And the KT boundary, this is a famous marker bed because it marks the end of the Cretaceous, which is the last period of the Mesozoic era, and the beginning of the Tertiary, which is the first period of the Cenozoic era. And if you're familiar with this Mesozoic era, it contains the three periods, the Triassic, Jurassic, and Cretaceous, and it's famous because it is the era of the dinosaurs. And so this KT boundary, this marker bed that marks the end of the Mesozoic, also marks a major mass extinction of its past, the Mesozoic mass extinction, which brought about the extinction of most of the dinosaurs. And so it's an example of a very famous marker bed, and it's distributed over a large portion of the globe because it is the product of the fallout of a large meteorite impact or asteroid impact. And that debris, that ejecta from the impact, was thrown up into the atmosphere, and it was distributed throughout the atmosphere and settled out all over the planet, forming this marker bed. So anywhere you go, if you find this key bed, this marker bed, the KT boundary, that you know you are looking at 65 million years ago, because that's whenever this event happened. So it gives us a reference in multiple parts of the planet. So correlating rock units, like we talked about a little while ago, it's helpful in putting the larger picture together. So when we correlate rock units, we can not only can get an idea of what happened in one location in the past, but we can get an idea what happened in a much broader region if we can connect the rocks from one location to another. For example, the Colorado Plateau, which is a region in the southwest part of the United States, it is known for its very beautiful layers of sedimentary rock. These sedimentary rocks were deposited on an ancient seafloor, and this sea was in existence for several hundred millions of years. Most of the continent of the United States was covered by a shallow ocean for hundreds of millions of years. Only the forming Rockies and the Appalachians were above sea level. And so Bryce Canyon, Zion National Park, and the Grand Canyon National Park, these are three locations well known for their beautiful sedimentary rocks. Excuse me, but the rocks at Bryce Canyon are the youngest. So we see these beds of sedimentary rock. This is a geologic cross-section from Bryce Canyon. And the oldest exposed sedimentary rocks at Bryce Canyon, they correlate with the youngest exposed sedimentary rocks at Zion National Park, which tells us that, these are the same rocks, have the same fossils in them, have the same type of sediment, and so forth. So we can correlate these rocks and say, well, if these are the same rocks, they formed at the same time. So by correlating these rocks together, this Carmel Formation and Navajo sandstones, you can then make the assumption, well, if these rocks are above here, these younger rocks at Bryce Canyon, then chances are they used to be at Zion National Park. They have just been weathered and eroded away. And that these older rocks that are exposed at Zion National Park, chances are they are here in Bryce Canyon, but just haven't yet been exposed by weathering and erosion. And then you can see the oldest exposed sedimentary rocks at Zion National Park, this Kabab limestone. It correlates with the youngest exposed sedimentary rock at the Grand Canyon. So we correlate them together. So that allows us to map all the younger sedimentary rocks at Bryce Canyon and Zion National Park to the Grand Canyon. So these rocks probably were here at one time. They've just been weathered and eroded away. At the same time, the older rocks that are exposed to the Grand Canyon are probably located at Zion National Park and Bryce Canyon, but are just, as before, haven't been exposed by erosion yet. So instead of just getting a piecewise view of geologic past at each location, by correlating the rock units from one location to the other, we are able to put together a larger window of time, or what happened for a larger period of time in this whole entire area. And so we can see what's happened since pretty much the beginning of the Cambrian to near recent times, so tens of millions of years ago. So we're looking at roughly 500 million years worth of history here in these sedimentary rocks, these three locations in the Colorado Plateau. So that allows us, so we see this large cross-section of the area up here. We're able to map these deeper sedimentary rocks in this cross-section because of correlating rock units. Say, well, these rocks, older rocks, are exposed here at the Grand Canyon. Chances are that they are over here too. And we make that assumption because of the principles of relative dating, that we say that the sedimentary rocks are laterally continuous, so they probably extend laterally. And that's why we're able to map them down there. So that's it for geologic dating. And I'm going to post, I'm pretty sure, a short lecture beginning a lecture on crustal deformation and mountain building. Thank you very much.